Welcome back. I hope you're all having a lot of fun. Today we're going to take a look at something that is extremely important, especially when applying time series to physical sciences, and that is regression. But first I'm going to remind you of something. Identifying a time series process really boils down to figuring out the joint probability function for all x values at all moments of time. If x is continuous, it comes to a PDF or probability density function. If x is discrete, it comes to a PMF or probability mass function. A deterministic process means that the data values at some time are some function of time. So the probability function is a delta function of x minus that function of time. And the joint probability function for all the values of a deterministic process is the product of the individual probability functions. I just wanted to remind you of that so it could burn into your brain. With that out of the way, let's get on to regression. We often look at data which we think shows a deterministic signal, not just something random. It's important to be aware of the difference between deterministic and stochastic. A deterministic signal means that if you repeat the exact same experiment, you're going to get the exact same result. The deterministic part is the part that comes out exactly the same every time you run the process. A stochastic process has randomness to it, so that's the part that can come out differently on different realizations of the process. In fact, when it comes to the deterministic part, we often have reason to believe that we know the form of that signal. But maybe the form is something simple like it's following a straight line, which would have a certain intercept and a certain slope. Those are parameters of the line. And we need to use the data to estimate the parameters of our model. This process can loosely be called regression. Now, there are many roads to regression, but by far the best known and the most common is least squares regression. There are lots of different kinds of regression, and we're going to look at many different kinds. We're also going to look at least squares regression in incredible detail, but those are coming later on. Today we're going to take a first look at least squares regression so you get an idea of what it's really about. Suppose, for instance, that we believe the data follow a straight line. But in addition to following a straight line, there's also random noise. It could be measurement error. Or it could be that the noise is part of the actual physics, but there's this underlying trend which follows a perfectly straight line and doesn't deviate it from it. So our data follows this equation. The data value is some intercept plus some slope times the time plus some stochastic part, which I'll call the noise. We're going to deal with the case that the noise is zero mean white noise, and that the variance of the noise is sigma squared. That's just a name for it. Since the noise we're assuming is white noise, that means that the covariance between values is given by this. It's the covariance between epsilon j and epsilon k is sigma squared times delta sub jk, where delta is the Kronecker delta. That's just a special symbol for a matrix which is equal to 1 on the diagonal when j equals k, and is equal to 0 everywhere else. Now, not all noise is white noise. In fact, there's a lot of non-white noise. That's going to be an important subject we'll deal with much later. Well, not much later, but we'll deal with it quite a bit later. But for now, we want to keep things simple, so we're going to consider the case of white noise. Now, for any given set of parameters, beta naught, the intercept, and beta 1, the slope, that gives us a model of the behavior of the data. The model, of course, enables us to compute what the data values would be in the absence of noise. We can take the difference between the observed values and what they would have been for a particular model, and we can use that to define residuals for that particular model, that particular value of the parameters, intercept, and slope. Now, let's take the sum of the squares of all the residuals, and let's use that as a measure of the total error of the model. The method of least squares selects the parameters beta naught and beta 1, the intercept and the slope, which give the smallest total error, or sum of squared residuals. That's where the name least squares comes from. How do we find those parameter values? Well, we just find the values for which the partial derivatives of the sum of squared residuals with respect to each and every parameter are equal to 0. For instance, for the intercept parameter, we have this equation right here. This is the partial derivative of the sum of squared residuals with respect to beta naught, and that has to equal 0. For the slope parameter, here is the partial derivative of the sum of squared residuals with respect to beta 1, and that has to equal 0. Now, these are two equations in two unknowns, beta naught and beta 1, and that enables us to determine the parameters. Now, I'm going to rewrite these equations in this way. I've just kind of rearranged a few terms, and it turns out that they are equivalent to the sum of all the x values is equal to this quantity. By the way, I was able to do that from that because beta naught is a constant. It doesn't change over time. So the sum over all n values of that constant is just n times that constant. I also can rearrange the other equation to get that the sum of time times data value is equal to this quantity. Now, these two equations in two unknowns are linear in the parameters, beta naught and beta 1, and that's what makes this process linear least squares. Now, for conceptual simplicity, I'll divide the equations by n. I'll also define the average data value x bar, which is just the average of all the x values, and the average time t bar, which is just the average of all the times. That enables me to write the equations like this, which are easy to write and probably look a little bit simpler. I can also write them like this. Instead of writing x bar for the average x value, I can just write angle brackets around the x, angle brackets around the t for the average time value, angle brackets around t times x for the average time times data value, angle brackets around t squared for the average time squared value. Do keep in mind my convention for angle brackets, that since we're assuming that t sub n and x sub n are actual data rather than just an abstract process, the angle brackets indicate average values rather than expected values. Well, now we've got the equations and we can write them in matrix form. The top line of this matrix equation is really just the first equation. The bottom line is really just the second equation. These equations, this matrix equation, can be solved for the coefficients by multiplying both sides of it by the inverse of the matrix, and that gives us this. This is the solution to linear least squares for linear regression, that the intercept and slope are equal to this quantity times this matrix, matrix multiplied by this vector being the average x value and the average t times x value. Voila, there is our solution. By the way, knowledge of the coefficients, beta naught and beta 1, it tells us the straight line which best fits the data in the least squares sense. And since we're using a straight line as a model, this is called linear regression. We do need to be a little bit careful about terminology. In the name linear regression, the word linear refers to the fact that the model is a straight line. But in the name linear least squares, the word linear refers to the fact that the model is linear in its regression coefficients, beta naught and beta 1. Whatever those coefficients might refer to, it is linear in its parameters. So there's really a big difference conceptually between linear regression and linear least squares. Linear regression means you're using a straight line model. Linear least squares means you're using a model which might not be a straight line, but it is linear in its parameters. This is a common mistake. In fact, it happens quite a bit, surprisingly often, in actual published scientific research. Some researchers will make the mistake of saying that they've applied nonlinear least squares, when what they've actually done is used a nonlinear model They're using linear least squares because the model is linear in its parameters, but the model has terms which are not linear in the arguments. But they're still linear in their regression coefficients, so it's still linear least squares.